We're about to embark on a journey that will challenge everything you think you know about our home planet and the delicate balance that makes life possible. Tonight, we're exploring a question so mind-bending, so catastrophically fascinating, that it touches the very foundations of physics, biology, and existence itself. What if Earth was as big as the Sun? It sounds simple enough, doesn't it? Just imagine our blue marble scaled up to match the brilliant star that gives us life. But as we'll discover together, this seemingly innocent thought experiment reveals secrets about gravity, atmosphere, and the razor-thin conditions that allow us to exist at all. If you find comfort in these gentle explorations of science, I'd be grateful if you'd consider subscribing and hitting that like button. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the cosmos as we unravel this mystery together. Let's begin with something that will put this entire journey in perspective. Picture yourself standing in an empty football stadium. Now imagine placing a marble at the center of the field. That marble represents Earth. To represent the Sun at the same scale, you'd need a sphere about 12 feet across, filling nearly the entire width of the stadium. The Sun is so massive that you could line up 109 Earths across its face. In terms of volume, you could fit 1.3 million planet Earths inside our star. But here's where our thought experiment becomes truly extraordinary. We're not just talking about making Earth a little bigger, or even a lot bigger. We're talking about increasing its size by a factor that defies human comprehension. The transformation we're imagining would fundamentally rewrite the laws of physics as they apply to our world. Now you might be thinking, surely if we just scaled everything up proportionally, things wouldn't change that dramatically, right? Perhaps gravity would be a bit stronger, the days might be longer, but surely life could adapt somehow. This is where our cosmic story takes a turn toward the profound and the terrifying. Because the universe doesn't work with simple proportions when we're dealing with forces as fundamental as gravity. Let me paint you a picture of the immediate aftermath of such a transformation. Imagine waking up one morning to find that overnight, our planet has quietly expanded to match the dimensions of our Sun. The first thing you'd notice, if you were somehow still conscious to notice anything at all, is that you can no longer move. In fact, you can no longer breathe. The gravity on the surface of a sun-sized Earth would be approximately 28 times stronger than what we experience today. 28 times. To put that in perspective, imagine trying to lift a coffee cup that suddenly weighs as much as a large dog. Imagine your own body weighing as much as a small car. Every step you tried to take would require the strength of lifting a refrigerator, but the reality would be far worse than merely struggling with heavy objects. The human body, evolved over millions of years under Earth's current gravitational conditions, would simply cease to function. Our skeletal system, our muscular system, our cardiovascular system, even our ability to breathe, all depend on the precise gravitational environment we've always known. Under 28 times normal gravity, your skeleton would be crushed under your own body weight within seconds. Your heart would be unable to pump blood against the increased gravitational force. Your lungs would collapse as your chest cavity compressed under the enormous downward pressure. Even lying flat on the ground wouldn't save you, as the pressure would be so intense that your entire body would be flattened against the surface like a pressed flower. And you wouldn't be alone in this fate. Every living thing on Earth would face the same instantaneous destruction. The mighty redwood trees that have stood for thousands of years would topple like matchsticks, their trunks snapping under gravitational forces. Their cellulose fibers were never designed to withstand. Every blade of grass, every flower, every towering oak would be pressed flat against the ground in a matter of seconds. The great blue whales in our oceans, already at the limit of what biological structures can support, even in the buoyancy of water, would be crushed by their own mass. Birds would fall from the sky, not just because flight would be impossible, but because their hollow bones would shatter under the increased gravitational stress. Even the landscape itself would transform beyond recognition. Mountains that took millions of years to rise would crumble, as their rocky foundations could no longer support their own weight. The familiar peaks and valleys that define our world's geography would flatten into a more uniform surface, unable to maintain their elevation against the crushing downward force. But the catastrophe wouldn't stop with the immediate crushing effects of enhanced gravity. The very air we breathe would become our enemy. The increased gravitational force would compress our atmosphere to densities never before experienced on any known planet. Near the surface, the air would become so thick and heavy that it would approach the density of liquid. Imagine trying to breathe underwater, but instead of water, you're surrounded by air so compressed that it behaves almost like a fluid. The atmospheric pressure at sea level would increase by factors we can barely calculate, creating an environment more hostile than the deepest ocean trenches. This atmospheric compression would trigger a cascade of climatic disasters. The dense air would create a greenhouse effect beyond anything our planet has ever experienced. Heat would be trapped so efficiently that surface temperatures would begin climbing toward levels that would make Death Valley seem like a pleasant spring day. Meanwhile, beneath our feet, the expanded Earth would be generating internal heat on a scale that dwarfs anything in our planet's history. A sun-sized Earth would contain vastly more radioactive material than our current world. The decay of these elements would pump enormous amounts of heat into the planet's interior, creating magma chambers of unprecedented size and violence. The geological consequences would be swift and merciless. Across the surface of this transformed world, hundreds of new volcanoes would erupt simultaneously. But these wouldn't be the isolated volcanic events we're familiar with from Earth's history. This would be a planet-wide eruption with lava flows, ash clouds, and pyroclastic flows covering virtually every square mile of the surface. The volcanic activity would pump massive quantities of carbon dioxide and other greenhouse gases into the already compressed atmosphere, accelerating the warming process and creating what geologists call a runaway greenhouse effect. This is the same process that transformed Venus from a potentially habitable world into the hellish furnace we observe today, but magnified beyond our most extreme models. As we contemplate these cascading disasters, it's important to understand that we're not just talking about a very bad day for planet Earth. We're describing the complete breakdown of every system that makes our world habitable. The delicate balance of atmospheric pressure, gravitational force, geological stability, and climatic regulation that allows life to exist would be shattered in a matter of hours. The transformation wouldn't just affect our planet in isolation. The gravitational effects would ripple outward through our solar system, disrupting the orbital dynamics that have remained stable for billions of years. Our moon, that faithful companion that has influenced our tides and stabilized our axial tilt throughout Earth's history, would face immediate doom. The enhanced gravitational pull of our expanded planet would overcome the Moon's orbital velocity within days. As our satellite spiraled inward, it would be subjected to tidal forces so extreme that they would literally tear it apart before it could impact our surface. The resulting debris field would rain down on our already devastated world for months, creating a bombardment that would make the asteroid impact that killed the dinosaurs look like a gentle spring shower. But perhaps most haunting of all is the realization of how precisely calibrated our current existence really is. The size of our planet, the strength of our gravity, the density of our atmosphere, the distance from our sun, all of these factors work together in a harmony so delicate that even small changes can have dramatic consequences. Scientists have calculated that if Earth were just 50% larger in diameter while maintaining the same density, we would already be unable to achieve spaceflight using conventional rockets. The escape velocity would be too great for chemical propulsion to overcome. A sun-sized Earth would have an escape velocity thousands of times greater than what any conceivable technology could achieve, effectively trapping any hypothetical survivors on the surface permanently. This brings us to one of the most sobering aspects of our thought experiment. Even if, through some miracle of adaptation, life could somehow survive the initial catastrophe of expansion, the resulting world would be completely cut off from the cosmos. There would be no possibility of space exploration, no chance of reaching other worlds, no opportunity to spread life beyond the confines of our transformed planet. The very concept of looking up at the stars and wondering what lies beyond would become purely academic, as escape from such a massive world would be physically impossible. Any civilization that might somehow develop under such extreme conditions would be forever earthbound, trapped in a gravitational well so deep that even light would struggle to escape. As we continue our journey through this cosmic catastrophe, we'll explore how the internal structure of our planet would change, what would happen to our weather systems, and why the very atoms that make up our bodies might behave differently under such extreme conditions. We'll discover how this transformation would affect not just our world, but the entire solar system, and we'll uncover the remarkable precision required for planets to support life. But for now, as you settle deeper into this exploration, consider the miraculous nature of our actual existence. Every breath you take, every heartbeat, every moment of consciousness depends on the precise balance of forces that make our world exactly the right size, with exactly the right gravity, in exactly the right place in our solar system. The Earth beneath your feet isn't just a random ball of rock floating through space. It's a finely tuned system where countless variables work in perfect harmony to create the only known oasis of life in an otherwise hostile universe. And as we'll discover, that harmony is far more fragile than we might ever imagine. Discover, that harmony is far more fragile than we might ever imagine. The story of our transformed world grows even more extraordinary when we consider what would happen to time itself. As our planet expands to solar dimensions, the laws of physics would demand a dramatic change in how our world spins through space. You see, angular momentum must be conserved, and as Earth's mass spreads across a vastly larger sphere, its rotation would slow to a crawl. Where we currently experience a 24-hour cycle of day and night, our sun-sized Earth would rotate so slowly that a single day would stretch across weeks or even months of our current time. Imagine the sun rising on a Monday morning and not setting until the following month. Picture the profound strangeness of living through weeks of continuous daylight, followed by weeks of endless night. This dramatic change in our planet's rotational period would unleash weather systems of unimaginable violence. The side of our world facing the sun would bake under continuous solar radiation for weeks on end, while the night side would freeze in perpetual darkness. Temperature differences between these two hemispheres would be so extreme that they would dwarf anything we've ever experienced on Earth. The day side would become a furnace, with temperatures climbing far beyond what any known material could withstand. Metals would melt, rocks would soften, and the very air would shimmer with heat distortions that would make the surface appear to ripple like a mirage. Meanwhile, the night side would plunge into a cold so intense that even the gases in our atmosphere would begin to freeze and fall as snow. But nature abhors such extremes, and our planet's atmosphere would attempt to balance these temperature differences through wind patterns that defy description. Imagine hurricanes that span entire continents, with wind speeds that could level mountains and tear apart the strongest materials known to science. These atmospheric rivers of superheated and supercooled air would race around our planet at velocities that would make our current weather systems seem like gentle summer breezes. The very concept of seasons would become meaningless on such a world. Instead of the gentle transitions from spring to summer to autumn to winter that regulate life on our current planet, inhabitants of this transformed Earth would experience only the brutal extremes of eternal day or eternal night, with violent transition zones where these two realms meet. Deep within our expanded planet, equally dramatic changes would be taking place. The core of our sun-sized Earth would experience pressures so intense that they would approach the conditions found in white dwarf stars. The iron that makes up Earth's core would be compressed to densities that barely exist anywhere else in the universe outside of the hearts of dying stars. Under such extreme pressure, the familiar properties of matter would begin to break down. The iron core might solidify completely, shutting down the convection currents that generate our planet's protective magnetic field. Without this magnetic shield, our world would be defenseless against the constant bombardment of cosmic radiation and solar wind that currently gets deflected harmlessly into space. This loss of magnetic protection would have consequences that ripple through every aspect of our planet's ability to sustain any form of life. The solar wind, that stream of charged particles flowing constantly from our sun, would begin stripping away our atmosphere molecule by molecule. What happened to Mars over millions of years would happen to our transformed Earth in mere centuries or decades. But even more fascinating than these destructive processes are the exotic physical phenomena that might begin to occur within our planet's core. The temperatures and pressures at the center of a sun-sized Earth might approach those needed for nuclear fusion reactions. While our planet lacks the hydrogen-rich composition that powers our actual sun, the carbon and heavier elements in Earth's interior might begin undergoing fusion processes that have never been observed on any planetary body. Imagine our planet beginning to glow from within, not from reflected sunlight, but from nuclear fires burning at its heart. The boundary between planet and star would begin to blur as our world started generating its own energy through nuclear processes, though it wouldn't achieve the sustained hydrogen fusion that powers true stars. It might become something entirely unprecedented in our understanding of planetary science. This internal energy generation would add yet another layer to the catastrophic conditions on our planet's surface. Heat flowing upward from these deep fusion reactions would combine with the heat from radioactive decay and the greenhouse effects of our compressed atmosphere to create surface temperatures that would rival the interior of a furnace. Any water that might have survived the initial gravitational crushing would instantly flash into superheated steam. But even this steam wouldn't last long in the extreme conditions. The molecules themselves would begin to break apart under the intense heat and pressure, dissociating into their component hydrogen and oxygen atoms before being stripped away by the fierce atmospheric dynamics. The familiar blue marble we call home, with its swirling white clouds and deep blue oceans, would be transformed into something that glows red hot against the darkness of space. From orbit, if any observer could somehow survive to witness it, our planet would look more like a small, dim star than the world we know and love. Yet perhaps the most profound change would be to the very fabric of space and time around our planet. A mass as large as our Sun creates significant curvature in space-time itself. Clocks would run slower on the surface of our transformed Earth compared to locations farther away from its gravitational influence. Time dilation, effects that we typically associate only with extreme astrophysical objects, would become everyday reality for anyone somehow existing on such a world. This warping of space-time would affect not just the flow of time, but the behavior of light itself. Photons trying to escape from the surface would lose energy climbing out of the deep gravitational well, causing light to shift toward redder wavelengths. Our planet would literally redshift its own light, creating optical effects that would make the surface appear even more alien and strange. The mathematics of orbital mechanics around such a massive body would create entirely new possibilities for satellite behavior. Objects orbiting close to our transformed planet would experience such intense gravitational gradients that they would be stretched and compressed by tidal forces. The same forces that create our gentle ocean tides would become powerful enough to tear apart any solid object that ventured too close. But it's when we consider the effects on our solar system as a whole that the true scope of this transformation becomes clear. Our sun-sized Earth would no longer be a planet orbiting a star, but rather one member of a binary system. The gravitational dance between our transformed world and our actual sun would create orbital dynamics unlike anything currently seen in our cosmic neighborhood. The two massive bodies might begin orbiting around their common center of mass, creating a system where neither object clearly dominates the other gravitationally. This would fundamentally alter the orbits of every other planet in our solar system. Mercury, Venus, and Mars would find themselves caught in a complex gravitational tug-of-war between these two massive objects. Some planets might be ejected from the solar system entirely, flung into the cold depths of interstellar space by the chaotic gravitational interactions. Others might find new, highly elliptical orbits that would send them careening between the inner and outer regions of our transformed solar system. The orderly, predictable planetary orbits that have remained stable for billions of years would dissolve into cosmic chaos. Jupiter and Saturn, those gas giant guardians that currently protect the inner solar system by capturing or deflecting dangerous asteroids and comets, would see their own orbits destabilized, The asteroid belt between Mars and Jupiter might be scattered, sending rocky projectiles throughout the solar system in unpredictable trajectories. The very concept of a habitable zone, that narrow band around our sun where liquid water can exist, would become meaningless in such a chaotic system. Planets would no longer maintain steady distances from heat sources, instead following wild orbital paths that would alternately freeze and fry any worlds that might somehow retain their atmospheres. Even the outer planets, Uranus and Neptune, those distant ice giants that seem so removed from the affairs of the inner solar system, would feel the gravitational influence of our transformed Earth. Their orbits might shift dramatically, potentially affecting the Kuiper belt and sending icy bodies cascading toward the inner planets in a bombardment that would last for millions of years. As we contemplate these cosmic consequences, we begin to understand that the question of what would happen if Earth was as big as the Sun isn't just about our planet alone. It's about the intricate web of gravitational relationships that bind our solar system together, and how the change of a single variable can unravel billions of years of celestial stability. The delicate gravitational balance that allows our solar system to function as a stable, predictable environment for planetary development would be shattered completely. In its place would emerge a chaotic system where nothing could be predicted, where the very concept of stable planetary climates would become impossible. This cosmic catastrophe would unfold over timescales both immediate and extended. The initial crushing effects would be instantaneous, but the orbital disruptions would play out over thousands or millions of years, creating an ever-changing celestial environment where no world could maintain the stable conditions necessary for life to develop or survive. And yet, through all this destruction and chaos, we can find a profound appreciation for the remarkable precision of our actual solar system. Every planet orbits at just the right distance, with just the right mass, influenced by just the right gravitational forces to create a stable, long-term environment where life could emerge and flourish. The Earth beneath your feet exists in a state of perfect cosmic balance, neither too large nor too small, neither too close to our sun nor too far away, with a moon of just the right size to stabilize our planet's rotation and create the tidal forces that may have helped life emerge from our ancient oceans. As we continue our exploration of this hypothetical catastrophe, we'll delve even deeper into the physical impossibilities that would emerge, examining how the very atoms and molecules that make up matter would behave differently under such extreme conditions, and discovering why the universe seems to have such precise requirements for the emergence of complexity and life. The atomic dance that underlies all matter would transform into something unrecognizable under the extreme conditions of our sun-sized Earth. The very building blocks of reality would begin to behave in ways that challenge our understanding of chemistry and physics. In the crushing depths of our transformed planet, electrons would be forced into new orbital configurations around atomic nuclei, creating exotic forms of matter that exist nowhere else in our current solar system. Under pressures exceeding those found in the cores of massive stars, the familiar periodic table of elements would become a mere suggestion rather than a fundamental law. Carbon atoms, the backbone of all life as we know it, would be compressed into diamond-like structures of unprecedented density. But even diamond, that hardest of natural substances, would eventually yield to the relentless gravitational crushing, forming new crystalline arrangements that have never been observed in terrestrial laboratories. The water molecules that make up 70% of our bodies would find themselves in an impossible situation. Under the extreme pressures near the surface of our transformed world, water would exist in phases that don't appear on any standard phase diagram. Ice would form at temperatures that would normally melt steel, while liquid water would require pressures that would instantly crush any container designed to hold it. Oxygen, that life-giving gas we breathe without thinking, would undergo transformations that would make it unrecognizable. The familiar diatomic oxygen molecules would be forced together into larger, more complex structures. Some of these high-pressure forms of oxygen would be so reactive that they would spontaneously ignite any organic material they encountered, turning the very air into a fire that could never be extinguished. The DNA that carries the genetic instructions for all life on Earth would face destruction at the molecular level. The delicate hydrogen bonds that hold the famous double helix together would be disrupted by the extreme conditions, causing genetic information to unravel like a rope whose fibers have been cut. Even if life could somehow adapt to the crushing gravity, the fundamental chemistry of heredity would become impossible. But perhaps most fascinating of all would be the behavior of the electromagnetic forces that govern how atoms interact with each other. Under the extreme conditions of our transformed planet, these forces would begin to operate differently, changing the very rules by which matter assembles itself. Chemical bonds that are stable under normal Earth conditions would become impossible, while new types of molecular interactions would emerge that have no analogy in our current understanding of chemistry. The metals that form the backbone of our technological civilization would undergo phase transitions that would render them unrecognizable. Iron, the element that makes up the bulk of our planet's core and gives strength to our steel structures, would be compressed into forms so dense that a teaspoon would weigh as much as an automobile. These ultra-dense metals would possess properties that seem almost magical by our current standards, conducting electricity and heat in ways that defy our normal expectations. As we venture deeper into the heart of our transformed planet, we encounter temperatures and pressures that approach the conditions found in the interiors of massive stars. Here, the normal rules of matter begin to break down entirely. Electrons, those fundamental particles that orbit atomic nuclei and create the chemical bonds that hold everything together, would be stripped away from their parent atoms by the sheer intensity of the environment. In this electron-degenerate matter, the familiar concepts of solid, liquid, and gas would lose all meaning. Matter would exist in a state that physicists call a plasma, where atomic nuclei swim freely in a sea of unbound electrons. This is the same state of matter that exists in the cores of white dwarf stars, those incredibly dense remnants of dead suns that pack the mass of our entire sun into a sphere no larger than Earth. The nuclear forces that hold atomic nuclei together would begin to play an increasingly important role under such extreme conditions. In the deepest regions of our transformed planet's core, temperatures might climb high enough for nuclear fusion reactions to begin. Carbon nuclei, created in the hearts of ancient stars and now compressed to unprecedented densities, might begin fusing together to form heavier elements like neon and magnesium. These fusion reactions would release enormous amounts of energy, adding yet another source of heat to our already blazing planet. The energy output from these deep nuclear fires would dwarf the heat generated by radioactive decay, creating temperatures that would make the surface of the sun seem cool by comparison. Our planet would begin to shine with its own internal light, powered not by reflected sunlight, but by nuclear reactions in its core. This internal energy generation would create convection currents unlike anything seen in planetary science. Vast plumes of superheated plasma would rise from the core toward the surface, while cooler material would sink downward in a cycle that would remix the planet's interior on timescales measured in years rather than millions of years. The geology we understand, with its slow processes of mountain building and continental drift, would be replaced by a dynamic system that reshapes itself constantly. The magnetic field generated by such intense convection would be equally extraordinary. Instead of the relatively gentle magnetic environment that currently protects Earth from cosmic radiation, our transformed planet would generate magnetic fields millions of times stronger than anything we've ever measured. These fields would be so intense that they would affect the behavior of atoms themselves, splitting spectral lines in ways that would make the planet's light appear completely alien to any observer. Yet even as these nuclear fires burn in the deep interior, the surface of our world would present its own catalogue of impossibilities. The atmospheric dynamics driven by the extreme day-night cycle would create weather patterns that challenge the very concept of meteorology. Hurricanes spanning entire continents would be just the beginning of the atmospheric chaos. The temperature differential between the day and night sides would drive winds at speeds that approach significant fractions of the speed of sound. These hypersonic atmospheric rivers would carry enough kinetic energy to level mountains and reshape continents. The collision zones, where hot and cold air masses meet, would generate pressure waves that would propagate through the planet's crust like continuous earthquakes. Lightning storms in such an atmosphere would produce electrical discharges that dwarf anything seen on our current Earth. Individual lightning bolts would carry enough energy to power entire cities, creating electromagnetic pulses that would affect the planet's magnetic field itself. The constant electrical activity would ionize much of the atmosphere, creating an environment where normal radio communication would be impossible due to the continuous electromagnetic interference. The very concept of weather forecasting would become meaningless in such an environment. The chaotic dynamics of the atmosphere would make it impossible to predict conditions more than hours in advance. Each storm system would contain enough energy to alter global atmospheric patterns, creating a cascade of unpredictable changes that would ripple around the planet for years. In the transition zones between the day and night hemispheres, where the temperature gradients are steepest, we would witness phenomena that have no names in our current vocabulary. Atmospheric tides driven by temperature differences would create pressure waves that circle the planet like sound waves in air, but with amplitudes measured in thousands of pounds per square inch, rather than the tiny fluctuations we associate with acoustic phenomena. These pressure waves would interact with the planet's rotation and magnetic field in ways that would create new types of atmospheric dynamics. Spiral patterns hundreds of miles across would form and dissipate in the space of hours, driven by forces that combine thermal energy, magnetic fields, and the Coriolis effect in unprecedented ways. The atmosphere would become a constantly shifting maze of temperature zones, each with its own unique chemistry and physics. The water cycle, that fundamental process that distributes moisture around our current planet and makes complex weather patterns possible, would be transformed beyond recognition. Instead of the gentle evaporation and condensation that creates our clouds and rain, we would see explosive phase transitions where entire atmospheric regions would flash between liquid and gas states in moments. Steam eruptions from the day side would launch water vapor hundreds of miles into the atmosphere, where it would encounter the frigid conditions at high altitude and condense into ice crystals of unprecedented size. These massive ice formations would then fall toward the surface like crystalline meteors, each one carrying enough kinetic energy to create impact craters when they struck the ground. The very air itself would become a hazardous environment in ways we can barely imagine. The extreme compression near the surface would create pockets of atmosphere so dense that they would behave more like thick fluids than gas. Moving through such air would be like swimming through honey, if honey could also burn you with its temperature and crush you with its pressure simultaneously. Breathing would be impossible, not just because of the pressure, but because the chemistry of respiration depends on specific partial pressures of oxygen and carbon dioxide. Under the extreme conditions of our transformed atmosphere, these gases would exist in forms and concentrations that would be toxic to any life form we can conceive of. The very act of drawing breath would be like inhaling molten metal mixed with acid. Yet perhaps the most alien aspect of our transformed world would be the optical phenomena created by the extreme atmospheric conditions. Light traveling through air of such varying density would be bent and twisted in ways that would create mirages and optical illusions on a planetary scale. The day side might appear to observers to be a shimmering, ever-changing landscape where nothing appears solid or stable. These atmospheric lensing effects would make navigation impossible by visual means. The horizon would shift and distort constantly, creating the illusion that the landscape was flowing like water. Objects in the distance would appear to float, stretch, or multiply as light rays followed curved paths through the density gradients in the air. The night side would present its own optical mysteries. The extreme cold would cause portions of the atmosphere to condense and fall as snow. But this wouldn't be the gentle snowfall we know. Entire atmospheric layers would collapse simultaneously, creating avalanches of frozen air that would cascade toward the surface at tremendous speeds. The impact of these atmospheric avalanches would generate their own weather patterns, creating secondary storms that would propagate around the planet. As we contemplate these atmospheric impossibilities, we begin to understand that the familiar blue sky we take for granted is the result of incredibly precise conditions. The density, composition, and temperature of our current atmosphere exist within narrow ranges that allow light to travel in straight lines and chemical processes to proceed in predictable ways. Our transformed Earth would have an atmosphere that operates according to principles more similar to the interiors of gas giant planets than anything we recognize as planetary weather. The boundary between atmosphere and surface would become blurred as the extreme pressure would compress gases to near liquid densities, while the extreme heat would keep even solids in semi-molten states. The aurora phenomena that currently create beautiful light displays in our polar regions would be transformed into planet-wide electromagnetic storms. The intense magnetic field of our expanded world would interact with the solar wind to create continuous displays of light that would be visible even through the thick, distorted atmosphere. These auroras would carry enough energy to heat the upper atmosphere to temperatures comparable to stellar coronas. But even as we catalogue these atmospheric catastrophes, we must remember that we're describing a world where the very concept of a surface becomes questionable. The extreme conditions would blur the boundaries between solid Earth, liquid ocean, and gaseous atmosphere. Our planet would become something more like a layered fluid, with different zones characterized by different states of matter, rather than the clear distinctions we currently understand. The geological processes that shape planetary surfaces would be accelerated to timescales that would make continental drift look like rapid motion. Entire mountain ranges would rise and fall in matters of years, rather than millions of years. The familiar processes of erosion and sedimentation would be replaced by mechanisms involving plasma flows and electromagnetic forces that have no analogy in current geological science. As our exploration of this impossible world continues, we begin to see that the question of what would happen if Earth was as big as the Sun reveals something profound about the nature of planets themselves. There are fundamental limits to how large a rocky world can become before it transitions into something entirely different, something that exists in the realm between planets and stars and follows rules that we're only beginning to understand. The transformation of our world would ripple outward through the cosmos in ways that challenge our understanding of celestial mechanics. Picture the moment when our expanded Earth first exerts its newfound gravitational influence on the delicate orbital ballet that has governed our solar system for billions of years. The effects would cascade through space like dominoes falling in slow motion across astronomical distances. Venus, our closest planetary neighbor, would be among the first casualties of this cosmic reorganization. Currently orbiting the Sun in a path that brings it within 25 million miles of Earth at its closest approach, Venus would suddenly find itself caught between two massive gravitational influences. The elegant elliptical orbit that has remained stable since the formation of our solar system would begin to stretch and distort as our transformed planet's gravity tugged at it with unprecedented force. The mathematics of orbital mechanics tell us that Venus would likely be ejected from its current path within decades of our transformation. Either it would spiral inward toward the Sun, experiencing temperatures that would vaporize even its thick carbon dioxide atmosphere, or it would be flung outward into the cold depths of the outer solar system, where it would freeze into a lifeless ice ball drifting through eternal darkness. Mars, that rusty red world that has captured human imagination for centuries, would face an equally dramatic fate. The planet that currently orbits in a predictable pattern beyond Earth's orbit would find itself in gravitational free fall as the stable three-body system of Earth, Mars, and the Sun collapsed into chaos. Computer simulations of such scenarios suggest that Mars would follow one of several catastrophic paths, none of them conducive to the preservation of any potential life that might exist in its subsurface environments. The asteroid belt, that ring of rocky debris between Mars and Jupiter, that currently serves as a cosmic museum preserving materials from the early solar system, would be scattered like leaves in a hurricane. These ancient remnants of planetary formation, some the size of mountains and others no larger than pebbles, would be hurled throughout the solar system by the competing gravitational forces of our transformed Earth and the Sun. Some asteroids would rain down upon the inner planets in a bombardment that would dwarf the late heavy bombardment that scarred the Moon and Earth 4 billion years ago. Others would be accelerated to such high velocities that they would escape the solar system entirely, carrying with them the only physical evidence of our solar system's early history, and perhaps the only samples of primordial material that future civilizations might have used to understand their origins. Jupiter, that massive guardian of the outer solar system, would itself become unstable despite its enormous size. The gas giant that currently acts as a cosmic vacuum cleaner, protecting the inner planets by capturing or deflecting dangerous comets and asteroids, would find its own orbit perturbed by the gravitational chaos unleashed by our transformation. The careful resonances that currently govern the orbits of Jupiter's 4 major moons would be disrupted, potentially sending these ice-covered worlds on collision courses with each other or ejecting them into interstellar space. The Great Red Spot, that massive storm system that has raged in Jupiter's atmosphere for centuries, might finally be disrupted by the gravitational tidal forces exerted by our transformed Earth. The delicate atmospheric dynamics that maintain this enormous weather pattern depend on Jupiter's stable rotation and orbital characteristics, both of which would be fundamentally altered by the new gravitational environment. Saturn's magnificent ring system, those countless particles of ice and rock that create one of the most beautiful sights in our solar system, would face complete destruction. The gravitational perturbations would cause the ring particles to either spiral inward towards Saturn's surface or scatter outward into space. The shepherd moons that currently maintain the sharp edges of Saturn's rings would be unable to perform their gravitational housekeeping duties as their own orbits became chaotic and unpredictable. Even the distant ice giants, Uranus and Neptune, would feel the effects of our transformation. These worlds, so far from the Sun that they receive almost no solar heat and exist in a perpetual deep freeze, would find their orbital periods altered as the gravitational center of mass of the solar system shifted dramatically. The carefully balanced system that has allowed these planets to maintain stable orbits for billions of years would be thrown into disarray. The Kuiper Belt, that vast collection of icy bodies beyond Neptune's orbit that includes Pluto and thousands of other dwarf planets and comets, would be transformed from a relatively stable reservoir of frozen materials into a chaotic swarm of projectiles. Some of these objects would be hurled inward toward the Sun, creating a comet shower that would last for millions of years. Others would be accelerated to velocities sufficient to escape the solar system entirely, carrying with them water ice and organic compounds that might represent our solar system's only contribution to the interstellar medium. The very concept of the habitable zone, that narrow band around the Sun where liquid water can exist on planetary surfaces, would become meaningless in such a chaotic system. Planets would no longer maintain steady distances from our star, instead following wild elliptical orbits that would alternately freeze and fry any worlds that might somehow retain their atmospheres through the gravitational chaos. But perhaps most profound of all would be the realization that our transformed Earth would no longer be orbiting the Sun in any conventional sense. Instead, the two massive bodies would begin to orbit around their common center of mass, creating what astronomers call a binary system. The point around which both objects would orbit would lie somewhere between the two bodies, creating a gravitational environment unlike anything currently seen in our solar system. This binary configuration would create tidal forces throughout the solar system that would dwarf anything we currently experience. The gentle tides that currently raise and lower our oceans by a few feet would be replaced by gravitational effects that could stretch and compress entire planets. Any world caught between these two massive objects would be subjected to tidal stresses that would literally tear it apart. creating rings of debris similar to those around Saturn, but on a much more massive and violent scale. The orbital dynamics of such a system would be inherently unstable over long time periods. Unlike single-star systems where planets can maintain stable orbits for billions of years, binary systems with comparable masses create gravitational resonances and perturbations that make long-term stability impossible. Planets would be gradually ejected from the system or would spiral inward to destruction, leaving behind only a chaotic field of debris and scattered remnants. The Sun itself would be affected by this transformation in ways that would alter its fundamental characteristics. Currently, our star maintains its structure through a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion in its core. The gravitational influence of a nearby object with solar mass would create tidal forces within the Sun that could disrupt this balance. The surface of our star might develop massive prominences and solar flares as its outer layers respond to the gravitational tugging of our transformed Earth. The magnetic field lines that normally follow predictable patterns would be twisted and distorted by the external gravitational influence, creating solar storms of unprecedented magnitude that would affect every remaining object in the solar system. The solar wind, that stream of charged particles that flows constantly outward from the Sun, would be fundamentally altered by the presence of our transformed Earth. Instead of a relatively steady flow of particles expanding spherically outward, the solar wind would be channeled and focused by the gravitational and magnetic influences of the binary system, creating regions of space with particle densities far higher than anything currently experienced by the planets. These enhanced particle streams would strip away the atmospheres of any remaining planets at an accelerated rate, removing in decades what would normally take millions of years. The protective magnetospheres that currently shield planetary surfaces from cosmic radiation would be overwhelmed by the increased particle flux, leaving any surviving worlds defensively exposed to radiation levels that would sterilize their surfaces. The very nature of space weather would be transformed from the relatively predictable patterns we currently experience to chaotic, violent fluctuations that would make interplanetary travel impossible even for the most advanced civilizations. The electromagnetic environment of the solar system would become so turbulent that electronic equipment would fail within hours of exposure to the enhanced radiation fields. As we contemplate these cosmic consequences, we begin to understand that the stability of our current solar system is not an accident or a given, but rather an incredibly delicate balance that depends on every component being exactly the right size and in exactly the right place. The gravitational harmony that allows planets to maintain stable orbits for billions of years is so finely tuned that changing any single variable can unravel the entire system. Our transformed Earth would not just be a planet that had grown too large. It would be a cosmic disruptor that would fundamentally rewrite the rules by which our solar system operates. The orderly progression of planetary orbits that has provided a stable environment for the development of life would be replaced by a chaotic dance of gravitational forces that would make long-term planetary evolution impossible. The implications extend beyond our own solar system to our understanding of planetary formation and evolution throughout the universe. The discovery of exoplanets in recent decades has revealed solar systems with configurations that seem impossibly chaotic by our standards. with massive planets orbiting close to their stars, and planetary systems that appear to have been thoroughly scrambled by gravitational interactions. Our thought experiment suggests that such chaotic systems might be the result of planetary growth that exceeded the stability limits of rocky worlds. Perhaps somewhere in the galaxy, on worlds circling distant stars, similar transformations have occurred, turning stable planetary systems into the gravitational chaos that we observe through our telescopes. The precise conditions required for a stable, life-supporting solar system appear to be far more restrictive than we might have imagined. Not only must planets be the right size and in the right orbits, but they must remain within narrow limits throughout their entire evolutionary history. The growth of any planet beyond certain threshold values would trigger cascading instabilities that would doom any possibility of long-term biological evolution. This realization adds a sobering perspective to our search for life elsewhere in the universe. The famous Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy, includes factors for the rate of star formation and the fraction of stars with planetary systems. But our exploration suggests that we might need to add additional factors for the probability that planetary systems remain gravitationally stable long enough for complex life to evolve. The window of opportunity for biological evolution might be far narrower than we have assumed, requiring not just the right initial conditions, but also the continued stability of those conditions over geological timescales. Our transformed Earth represents a cautionary tale about the fragility of the cosmic environment that makes life possible, reminding us that the stability we take for granted is actually an extraordinary and perhaps rare achievement in the universe. As our journey through this cosmic catastrophe continues, we will explore how the fundamental forces of nature themselves would be altered under such extreme conditions, examining the exotic physics that emerges when matter is compressed to densities that rival the interiors of stars, and discovering why the universe seems to impose such strict limits on the size and structure of worlds that can support the emergence of complexity and consciousness. The boundaries between the familiar forces that govern our everyday world would begin to blur and transform under the extreme conditions of our sun-sized Earth. The electromagnetic force that holds atoms together and creates the chemical bonds underlying all biological processes would find itself competing with gravitational effects so intense that they would fundamentally alter how matter behaves at the most basic level. In the crushing depths of our transformed planet's interior, the very concept of chemistry as we understand it would cease to exist. The electron shells that determine how atoms interact with each other would be compressed to the point where electrons begin to occupy the same space as atomic nuclei. This process, known to physicists as electron capture, would transform familiar elements into exotic isotopes that have never been observed under terrestrial conditions. The carbon atoms that form the backbone of all organic molecules would find themselves in an impossible situation. Under normal Earth conditions, carbon's 4 outer electrons allow it to form the complex chains and rings that make proteins, DNA, and all the other molecules of life possible. But under the extreme pressures of our expanded world, these electrons would be forced into new configurations that would make organic chemistry impossible. Picture the delicate double helix of DNA, that elegant spiral staircase that carries the genetic instructions for every living thing on our planet. The hydrogen bonds that hold the two strands of the helix together are among the weakest forces in chemistry, easily broken and reformed under normal conditions to allow genetic information to be read and copied. Under the crushing pressure of our transformed Earth, these gentle bonds would be overwhelmed by forces millions of times stronger, causing the very blueprint of life to unravel at the molecular level. But the destruction would extend far beyond individual molecules to affect the fundamental processes that make life possible. The delicate balance of osmotic pressure that allows cells to maintain their shape and function depends on precise gradients of concentration across cell membranes. Under the extreme conditions of our transformed world, these pressure differences would be overwhelmed by the ambient crushing force, causing every cell membrane to collapse and every cellular process to cease instantly. The proteins that catalyze biochemical reactions and provide structural support for living tissues would undergo what biochemists call denaturation, but on a scale that has never been observed in any biological system. These complex molecules, folded into precise three-dimensional shapes that allow them to perform their specific functions, would be crushed into random tangles of amino acids, destroying their ability to sustain any form of life. Even more fundamentally, the water molecules that make up the majority of all living tissue would be forced into exotic phases of matter that have only been created in laboratory experiments under the most extreme conditions. Ice would form at temperatures that would normally melt copper, while liquid water would require pressures that would instantly vaporize any biological tissue that might somehow survive the gravitational crushing. The familiar states of matter that we take for granted would be replaced by phases that exist nowhere else in our solar system. Scientists have discovered that water can exist in at least 18 different crystalline forms under various combinations of temperature and pressure. Our transformed Earth would create conditions where multiple exotic ice phases would exist simultaneously, creating a landscape where the fundamental properties of the most basic substance for life would be completely alien. The atmospheric gases that currently support life through respiration and photosynthesis would undergo equally dramatic transformations. Oxygen, that life-giving element that makes up 21% of our current atmosphere, would be forced into molecular configurations that have never been observed outside of high-energy physics experiments. Some of these high-pressure forms of oxygen would be so chemically reactive that they would spontaneously ignite any organic material they encountered, creating fires that could not be extinguished by any known method. Nitrogen, the inert gas that makes up the majority of our current atmosphere and provides the gentle pressure that allows our lungs to function, would be compressed into a form so dense that it would behave more like a liquid than a gas. Breathing such an atmosphere would be like trying to inhale honey, if honey could also poison you with its chemical reactivity and crush your lungs with its density simultaneously. The very concept of a breathable atmosphere would become meaningless under such conditions. The delicate partial pressures of gases that allow oxygen to dissolve in blood and carbon dioxide to be expelled from our bodies depend on specific ratios that exist within narrow ranges. Under the extreme compression of our transformed world's atmosphere, these gases would exist at concentrations that would be immediately toxic to any conceivable form of life. But perhaps most alien of all would be the behavior of the fundamental forces themselves under such extreme conditions. The electromagnetic force that governs how atoms interact would begin to compete with gravitational effects in ways that have never been observed on any planetary surface. In the deepest regions of our transformed world, gravity would become so strong that it would affect the behavior of individual atoms, causing electrons to follow paths that defy our normal understanding of quantum mechanics. The strong nuclear force that holds atomic nuclei together would find itself operating in an environment where gravitational compression approaches the densities found in neutron stars. Under such conditions, the boundaries between different types of matter would begin to blur, creating forms of material that exist nowhere else in the universe except in the hearts of collapsing stars. These exotic states of matter would exhibit properties that seem almost magical by our current standards of physics. Materials that conduct electricity with zero resistance, substances that flow without friction, forms of matter that exist in quantum superposition states visible to the naked eye. Our transformed Earth would become a laboratory for physics that pushes the boundaries of what we thought possible under natural conditions. The magnetic fields generated by the movement of these exotic materials would be equally extraordinary. Instead of the relatively gentle magnetic environment that currently protects Earth from cosmic radiation, our transformed planet would generate magnetic fields so intense that they would affect the behavior of light itself. Photons traveling through such strong magnetic fields would be bent and twisted in ways that would make the optical properties of our world completely alien. These intense magnetic fields would interact with the solar wind in ways that would create electromagnetic phenomena visible from space. Our planet would be surrounded by aurora displays that would dwarf anything currently seen in our polar regions, creating light shows that would be bright enough to illuminate the night side of our world and powerful enough to disrupt electronic equipment on neighboring planets. The interaction between these magnetic fields and the flow of exotic matter in our planet's interior would generate electrical currents of unprecedented magnitude. These currents would flow through the planet's core like lightning bolts the size of continents, releasing energy at rates that would make our current understanding of planetary energy budgets seem quaint by comparison. The heat generated by these electrical phenomena would add yet another source of energy to our already blazing world. Combined with the heat from gravitational compression, radioactive decay, and potential nuclear fusion reactions, our planet would begin to glow with its own light, becoming something that exists between the categories of planet and star that we use to classify celestial objects. From space, our transformed Earth would appear as a dim red star, pulsing with variations in brightness as the exotic weather patterns in its atmosphere created shadows and bright spots that would shift and change over periods of hours or days. The familiar blue marble that has been home to life for billions of years would be transformed into something that would be more at home in the catalogue of variable stars than in any survey of potentially habitable worlds. The gravitational effects of such a massive object would create tidal forces that would reach far into space, affecting the behavior of any remaining debris in our solar system. Asteroids and comets that ventured too close would be stretched and compressed by these tidal forces until they literally tore themselves apart, creating rings of debris around our transformed world that would rival the spectacular ring systems of the gas giant planets. These rings would not be the stable, long-lived structures that we observe around Saturn and Jupiter, but rather dynamic, chaotic systems where particles would constantly collide and fragment, creating a debris field that would extend millions of miles into space. The constant rain of this material onto our planet's surface would add to the already catastrophic conditions, creating impact events that would release enough energy to vaporize mountains and boil seas. The very concept of a stable surface would become questionable under such conditions. The boundary between the solid interior and the gaseous atmosphere would be blurred by the extreme pressure and temperature gradients, creating a world where matter exists in a continuous spectrum of states, from the plasma-like conditions at the core to the exotic atmospheric phases near what we might generously call the surface. Navigation on such a world would be impossible by any conventional means. The intense magnetic fields would disrupt compass readings, while the optical distortions created by the dense atmosphere would make visual navigation equally hopeless. Even the concept of up and down would become ambiguous in regions where the gravitational gradient is so steep that tidal forces would stretch any object into spaghetti-like shapes. The familiar geological processes that shape planetary surfaces over millions of years would be accelerated to timescales measured in hours or days. Continental drift would become continental racing, with entire land masses being reshaped by forces that would make earthquake and volcanic activity seem gentle by comparison. The very atoms that make up rock and metal would be rearranged continuously by the extreme conditions, creating materials with properties that have never been observed in terrestrial geology. Mountains would rise and fall like waves on an ocean, but waves made of molten rock and exotic metals flowing under gravitational forces that would dwarf anything currently seen on any planetary surface. The familiar landmarks that allow us to navigate our current world would be meaningless concepts on a planet where the landscape reshapes itself faster than any observer could possibly map or remember. Yet even as we catalogue these impossibilities, we begin to understand something profound about the universe we inhabit. The conditions that allow stable matter to exist, that permit complex chemistry to occur, that enable life to emerge and flourish, exist within incredibly narrow ranges. Step outside those ranges, and the familiar world of atoms and molecules and biological processes gives way to something alien and hostile to everything we recognize as the building blocks of existence. Our current Earth exists in a state of perfect balance, not just in terms of its orbit around the Sun or the composition of its atmosphere, but in the fundamental physics that govern how matter behaves under the specific conditions of pressure, temperature, and gravitational field strength that characterize our world. Change any of these variables beyond certain threshold values, and the very chemistry of life becomes impossible. This realization adds a new dimension to our appreciation of the remarkable circumstances that have allowed life to emerge and flourish on our planet. It's not enough that Earth be the right distance from the Sun, with the right atmospheric composition and the right amount of water. It must also be exactly the right size, with exactly the right gravitational field strength, to allow the delicate chemistry of biology to operate within the narrow ranges where complex molecules can form and persist. The Drake equation and other attempts to estimate the likelihood of life elsewhere in the universe may need to account for these additional constraints on planetary habitability. The window of conditions that permit not just liquid water, but also stable organic chemistry, may be far narrower than we have previously imagined, making Earth-like worlds even rarer and more precious than our most conservative estimates have suggested. As we continue our exploration of this impossible world, we will venture into the realm of exotic physics, where the familiar rules of matter and energy give way to phenomena that challenge our understanding of reality itself. We will discover how the fabric of space and time itself would be affected by such extreme conditions, and why the universe seems to impose such strict limits on the physical parameters that govern planetary formation and evolution. But perhaps most importantly, we will gain a deeper appreciation for the extraordinary set of circumstances that have allowed our small blue world to become the only known oasis of life in an otherwise hostile cosmos, and why the preservation of those delicate conditions may be the most important challenge facing our species as we venture forth into the universe beyond our home planet. The fabric of space and time itself would begin to warp and buckle under the gravitational influence of our transformed world, in ways that would make Einstein's most mind-bending predictions seem like gentle ripples on a calm pond. Picture spacetime as a vast, flexible sheet stretched taut across the cosmos, and our sun-sized Earth as a bowling ball placed upon that sheet. The curvature created would be so extreme that it would fundamentally alter how time flows and how light travels through the region surrounding our planet. Clocks on the surface of our transformed Earth would run significantly slower compared to timepieces located farther away from its gravitational influence. This time, dilation effect, predicted by Einstein's theory of general relativity, would mean that a person somehow surviving on our planet's surface would age more slowly than someone observing from a safe distance in space. What might feel like a single day to a surface dweller could correspond to weeks or months for an external observer. The implications of such extreme time dilation would ripple through every aspect of physical reality. Light itself would struggle to escape from the surface of our world, losing energy as it climbs out of the deep gravitational well. This gravitational redshift would cause all light emanating from our planet to appear shifted toward longer, redder wavelengths, making our world appear dimmer and more alien to any distant observer. The speed of light, that fundamental constant that sets the ultimate speed limit for information and causality throughout the universe, would appear to vary depending on the observer's location relative to our transformed planet. While light would still travel at its constant speed through the local fabric of space-time, the severe curvature caused by our world's immense gravity would make photons follow paths that seem impossibly curved to observers accustomed to the gentle gravitational environment of normal-sized planets. Communication between different regions around our transformed Earth would become a relativistic nightmare. Radio signals sent from one location to another would experience different amounts of time dilation depending on their path through the varying gravitational field. Messages could arrive before they were sent from certain reference frames, while from others, they might be delayed by hours or days, creating causality paradoxes that would make coordinated activity across the planet's surface impossible. The very concept of simultaneity would lose its meaning in such an extreme gravitational environment. Events that appear to happen at the same time for one observer would occur in different sequences for others, depending on their location within the gravitational field. The orderly progression of cause and effect that we take for granted in our everyday lives would be replaced by a relativistic chaos, where the sequence of events depends entirely on the observer's reference frame. But perhaps most extraordinary of all would be the emergence of what physicists call frame-dragging effects. The rotation of our massive world would literally drag space-time around with it, creating a gravitomagnetic field that would affect the motion of any object in orbit around our planet. Satellites would find their orbits precessing in ways that have no analogy in our current understanding of planetary dynamics, while the very geometry of space around our world would be twisted into helical patterns that follow our planet's rotation. These frame-dragging effects would create regions of space where it would be impossible for any object to remain stationary relative to a distant observer. The twisting of space-time would force everything within a certain distance of our planet to rotate along with it, creating what physicists call the ergosphere, a region where the normal concepts of space and time become hopelessly entangled. Within this ergosphere, the distinction between space and time coordinates would break down entirely. Directions that we normally think of as purely spatial would acquire temporal components, while time itself would take on spatial characteristics. An observer falling into this region would find that moving in certain directions through space would be equivalent to traveling backward in time, creating the possibility for closed time-like curves and all the paradoxes that such exotic geometry implies. The tidal forces generated by our transformed Earth would create gravitational gradients so steep that they would be detectable over interplanetary distances. Objects orbiting our world would be stretched and compressed by these tidal effects, with a violence that would tear apart any solid material known to science. Even spacecraft designed to withstand the most extreme conditions would be reduced to streams of atoms before they could complete a single orbit around our transformed planet. These tidal forces would extend far beyond the immediate vicinity of our world, affecting the orbital mechanics of objects throughout our solar system. The mathematical elegance of Kepler's laws, which have described planetary motion with perfect accuracy for centuries, would be replaced by chaotic dynamics that would make long-term orbital prediction impossible. Computer simulations of such systems would require processing power that exceeds anything currently available to humanity. The gravitational waves generated by the rotation and internal dynamics of our massive world would ripple outward through space-time at the speed of light, carrying away enormous amounts of energy and gradually slowing our planet's rotation. These waves would be detectable by gravitational wave observatories throughout the galaxy, announcing to any advanced civilizations that something extraordinary and catastrophic had occurred in our solar system. The amplitude of these gravitational waves would dwarf anything detected by current instruments like LIGO and Virgo. While those observatories can detect waves created by colliding black holes and neutron stars, the signals from our transformed Earth would be strong enough to affect the operation of sensitive equipment throughout the solar system. The constant background of gravitational radiation would make it impossible to conduct precision measurements of space and time in our local cosmic neighborhood. The magnetic field generated by our transformed planet would interact with these gravitational effects in ways that have never been observed anywhere in the universe. The motion of charged particles through the extreme space-time curvature would create electromagnetic phenomena that defy our current understanding of plasma physics. Auroras would become permanent features visible even in daylight, powered not just by solar wind, but by the exotic electromagnetic effects generated by curved space-time itself. These electromagnetic disturbances would propagate throughout the solar system as magnetospheric waves, disrupting the magnetic fields of other planets and creating radio interference that would make astronomical observations impossible from anywhere within our solar system. The delicate radio telescopes that currently allow us to study distant galaxies and search for signals from extraterrestrial civilizations would be rendered useless by the constant electromagnetic chaos emanating from our transformed world. The event horizon concept, usually associated with black holes, would begin to manifest around our planet in subtle but measurable ways. While our sun-sized Earth would not be massive enough to form a true event horizon, certain types of information and energy would find it increasingly difficult to escape from regions close to our planet's surface. High-frequency electromagnetic radiation would be particularly affected, creating dead zones where certain forms of communication would become impossible. The quantum vacuum itself would be affected by the extreme gravitational conditions, leading to phenomena that exist at the intersection of general relativity and quantum mechanics. Virtual particle pairs that normally appear and disappear in the quantum foam of empty space would be separated by the intense gravitational gradients, with one particle falling toward our planet, while its partner escapes to infinity. This process would cause our world to emit a form of Hawking radiation, gradually losing mass and energy to the surrounding space. The rate of this quantum evaporation would be extraordinarily slow by human standards, requiring timescales longer than the current age of the universe to have any significant effect. Nevertheless, the very fact that our planet would be emitting quantum radiation represents a fundamental transformation from a classical gravitational object to something that straddles the boundary between general relativity and quantum field theory. The exotic matter phases that would exist within our planet's interior would create gravitational anomalies that would be detectable from space. Regions where matter exists in states that have never been observed in terrestrial laboratories would generate gravitational signatures that would make our world's gravitational field far more complex than the simple inverse square law that governs the gravity of normal planets. These gravitational anomalies would create regions where spacecraft would experience unexpected accelerations and trajectory changes. Navigation through the space around our transformed Earth would require constant course corrections as vessels encountered gravitational eddies and currents that would push and pull them in directions that no amount of theoretical preparation could predict accurately. The very atoms that make up any surviving material on or around our planet would be affected by the extreme space-time curvature. Atomic clocks, those incredibly precise timepieces that form the backbone of modern navigation and communication systems, would run at different rates depending on their altitude above our planet's surface. The global positioning systems that we rely on for everything from navigation to financial transactions would become hopelessly inaccurate within hours of our transformation. Spectroscopy, the technique that allows astronomers to determine the composition and properties of distant objects by analyzing their light, would become impossible in the vicinity of our transformed world. The extreme gravitational redshift and the exotic electromagnetic effects would distort spectral lines beyond recognition, making it impossible to identify even the most common elements in any material near our planet. The concept of a stable reference frame would lose all meaning in such an environment. The rotating, curved space-time around our world would make it impossible to establish any coordinate system that remains valid for extended periods. What physicists call geodesic deviation would cause initially parallel paths to converge and diverge in ways that would make precise navigation or positioning impossible by any conventional means. Even the fundamental constants of physics would appear to vary depending on location and reference frame within our planet's gravitational influence. While these constants would remain truly constant when measured locally, the extreme curvature of spacetime would make measurements taken from different positions appear to show variations in values that we currently consider to be universal and unchanging. The philosophical implications of such extreme spacetime curvature extend far beyond the realm of physics. Our transformed Earth would create a region of space where the normal relationships between cause and effect, between observer and observed, between space and time, would be fundamentally altered. The common sense reality that governs our everyday experience would be replaced by something so alien that even our most advanced theories of relativity and quantum mechanics would struggle to provide complete descriptions. Any hypothetical observers attempting to study our transformed world from a safe distance would face challenges that go to the heart of what it means to make scientific measurements. The extreme gravitational lensing effects would distort their view of our planet, making it appear larger, smaller, or multiply imaged depending on their viewing angle. The time delays caused by gravitational effects would make it impossible to observe events in real time, creating a fundamental disconnect between observation and reality. The information paradox that physicists debate in the context of black holes would manifest around our transformed Earth in ways that would challenge our understanding of how information can be preserved in the universe. As material falls toward our planet's surface, the information content of that material would become increasingly redshifted and time-dilated from the perspective of external observers, raising questions about whether information can ever truly be lost, or whether it simply becomes inaccessible beyond certain limits. These relativistic effects would create natural laboratories for testing the most extreme predictions of Einstein's theory of general relativity. Phenomena that can currently only be studied around black holes and neutron stars would become accessible for detailed observation around our transformed planet. The scientific opportunities would be extraordinary, if only there were any way for observers to survive the journey to our gravitational neighborhood. The merger of space and time into a unified space-time continuum would become directly observable rather than remaining an abstract theoretical concept. The curvature would be so extreme that the geometric relationships between different regions would become visibly distorted, creating a landscape where the familiar Euclidean geometry of everyday experience would be replaced by the non-Euclidean mathematics of curved space-time. Yet perhaps the most profound realization would be that our transformed Earth represents a natural limit to how large rocky planets can become before they transition into something fundamentally different. The boundary between planet and star would be revealed as not just a matter of composition and nuclear fusion, but as a fundamental threshold in the geometry of space-time itself. Beyond certain mass limits, the very concept of a planetary surface becomes questionable, as space-time curvature creates conditions where matter and energy exist in states that have no analogy in our current experience. This cosmic catastrophe would serve as a stark reminder that the gentle space-time curvature we experience on our actual Earth is not just a minor correction to Newtonian physics, but rather a fundamental aspect of reality that becomes dominant when gravitational effects reach sufficient intensity. The delicate balance that allows stable planetary surfaces, predictable orbital mechanics, and the reliable flow of time that makes complex biological processes possible exists within incredibly narrow limits that we violate at our peril. Our exploration of these extreme relativistic effects reveals yet another layer of the remarkable fine-tuning that makes our actual Earth such an extraordinary oasis in the cosmos. Not only must our planet be the right size for biological chemistry and atmospheric retention, but it must also be small enough to avoid creating the exotic space-time geometry that would make the orderly progression of physical processes impossible. As we prepare to conclude our journey through this impossible world, we begin to see that the question of what would happen if Earth was as big as the Sun has revealed fundamental truths about the nature of reality itself, the limits of physical law, and the extraordinary set of circumstances that have allowed our small blue world to become the only known haven for life in an otherwise hostile universe. The stability and predictability that we take for granted are not natural features of the cosmos, but rather rare and precious exceptions to the chaos that dominates the universe at large. The delicate dance of planetary formation that created our current Earth represents one of the most remarkable achievements in cosmic engineering, a process so precise that it operates within tolerances that would make the finest Swiss watchmaker weep with envy. As we contemplate the catastrophic transformation we've explored tonight, we begin to understand that planets exist within what scientists call the planetary habitability zone. But this isn't just about distance from a star or atmospheric composition. There's a fundamental size limit, a cosmic boundary beyond which rocky worlds transition into something entirely alien. This threshold exists not because of arbitrary physical laws, but because of the deep mathematical relationships that govern how matter, energy, space, and time interact under increasingly extreme conditions. Our sun-sized Earth would cross this boundary so dramatically that it would redefine what we mean by the very concept of a planet. The process of planetary accretion that formed Earth billions of years ago was governed by gravitational forces that are perfectly balanced to allow rocky material to clump together without creating the extreme conditions we've explored tonight. During the early bombardment period, when asteroids and comets rained down upon our forming world, each impact added mass and energy to our growing planet. But this process had natural limits built into the physics of planetary formation. Had our planet continued growing beyond a certain threshold, the additional gravitational energy from incoming material would have begun heating our world to temperatures that would prevent the formation of a solid surface. The water that makes life possible would have remained as superheated steam in a thick atmosphere, creating conditions more similar to Venus than to the Earth we know. The delicate balance between gravitational heating and radiative cooling that allowed our planet to develop oceans and continents exists within remarkably narrow parameters. But size limitations extend far beyond questions of surface temperature and atmospheric retention. The very stability of rocky planetary crusts depends on gravitational forces remaining within specific ranges. Too little gravity and atmospheres escape to space, while volcanic activity diminishes to the point where essential geological recycling processes cease. Too much gravity and the weight of overlying rock creates pressures that prevent the formation of stable continental structures. The plate tectonic system that regulates Earth's climate through carbon cycling and maintains the chemical balance necessary for life depends on having just the right amount of internal heat and just the right gravitational field strength. Our transformed world would generate so much internal heat that plate tectonics would be replaced by continuous volcanic resurfacing, while the extreme gravity would prevent the formation of the rigid crustal plates that make continental drift possible. Even the formation of planetary magnetic fields requires precise conditions that exist only within narrow size ranges. Our current magnetic field is generated by convection currents in Earth's liquid outer core, driven by the gradual cooling and crystallization of iron at the boundary between the inner and outer core. This delicate process requires core temperatures and pressures that exist only in planets of specific size ranges. A sun-sized Earth would either have core temperatures so high that all iron remains liquid, preventing the crystallization that drives convection, or pressures so intense that the entire core solidifies, eliminating convection altogether. Either scenario would shut down the magnetic dynamo that protects our planet from cosmic radiation and prevents our atmosphere from being stripped away by solar wind. The mathematical elegance of these size limitations extends to the quantum mechanical processes that govern how atoms and molecules behave under different gravitational conditions. The electron shells that determine chemical bonding properties are affected by the local gravitational environment in ways that become significant only under extreme conditions. Our transformed Earth would create gravitational fields strong enough to measurably alter the energy levels of electrons in atoms, changing the fundamental chemistry that makes complex molecules possible. This quantum gravitational chemistry represents a frontier of physics that we're only beginning to understand. In the extreme environments of neutron stars and the hearts of massive planets, the familiar periodic table of elements becomes a rough approximation rather than a fundamental law. Chemical bonds that are stable under normal planetary conditions become impossible, while new forms of matter emerge that have no analogy in terrestrial science. The discovery of exoplanets in recent years has revealed that planetary systems throughout the galaxy exhibit enormous diversity in their configurations and characteristics. We've found planets larger than Jupiter orbiting closer to their stars than Mercury orbits our Sun, worlds where surface temperatures exceed the melting point of iron, and planetary systems where massive worlds migrate inward over time, disrupting any possibility of stable, life-supporting environments. These observations suggest that stable, Earth-like conditions may be far rarer in the universe than we initially hoped. The precise combination of planetary mass, orbital characteristics, stellar properties, and system architecture that allows rocky worlds to maintain stable climates over geological timescales appears to require an extraordinary alignment of circumstances that may occur in only a tiny fraction of planetary systems. Our thought experiment has revealed that planetary habitability is not just about finding worlds in the so-called Goldilocks zone where liquid water can exist. It's about discovering planets that exist within multiple overlapping zones of stability, gravitational zones where rocky surfaces can form and persist, magnetic zones where protective magnetic fields can operate, chemical zones where complex molecular processes can occur, and temporal zones where these conditions can remain stable for billions of years. The anthropic principle suggests that we observe our universe to have the properties it does because we exist to observe it. Universes with different physical constants or different relationships between fundamental forces might not allow the formation of stable stars, planets, or the complex chemistry necessary for life. Our exploration tonight suggests that even within our universe, with its apparently life-friendly physical laws, the range of conditions that actually permit biological evolution may be extraordinarily narrow. This realization carries profound implications for our understanding of our place in the cosmos and our responsibilities as perhaps the only known instance of conscious life in our local region of the galaxy. The Earth beneath your feet represents not just a world that happened to develop life, but possibly the only world within hundreds or thousands of light years where the precise combination of size, composition, orbital characteristics, and cosmic circumstances has allowed intelligence to emerge and contemplate its own existence. The fragility of these conditions becomes even more apparent when we consider how easily they could be disrupted. A nearby supernova explosion could strip away our protective ozone layer, while the gravitational influence of a passing star could destabilize planetary orbits throughout our solar system. The impact of a large asteroid or comet could trigger climate changes that would make our world uninhabitable for complex life forms. Yet despite this fragility, or perhaps because of it, life on Earth has demonstrated remarkable resilience and adaptability. Through 5 major mass extinction events and countless smaller catastrophes, biological evolution has found ways to survive and diversify. The tree of life has bent but never broken, always finding new paths forward even when established ecosystems collapsed and dominant species disappeared. This evolutionary resilience suggests that while the physical conditions necessary for life may be extraordinarily rare, life itself possesses an almost magical ability to adapt to changing circumstances and exploit new opportunities. The same creative forces that have produced the stunning diversity of life we see around us might be capable of surviving even moderate changes to planetary conditions, as long as the fundamental requirements for complex chemistry remain intact. But our exploration tonight has shown us that there are absolute limits beyond which no amount of evolutionary creativity could compensate for the breakdown of basic physical and chemical processes. A sun-sized Earth would not present life with new challenges to overcome, but would instead eliminate the very possibility of biological chemistry operating at the molecular level. This distinction between challenging environments and impossible environments helps us understand why astrobiologists are so focused on finding planets that closely resemble Earth in size, composition, and orbital characteristics. While life might be able to adapt to conditions quite different from those on our current world, it cannot violate the fundamental laws of physics and chemistry that govern how complex molecules form and interact. The search for extraterrestrial life has been guided by the principle of following the water, looking for worlds where liquid water could exist on planetary surfaces. But our journey through this cosmic catastrophe suggests that we should also be following the physics, searching for worlds where the gravitational, electromagnetic, and quantum mechanical conditions allow the emergence of the complex chemistry that makes life possible. This means looking not just for planets in habitable zones around their stars, but for worlds that exist within the narrow range of masses where rocky surfaces can form, where magnetic fields can operate, where plate tectonics can regulate climate, and where the fundamental chemistry of biology can proceed without interference from exotic physical effects. The James Webb Space Telescope and other advanced astronomical instruments are beginning to provide us with detailed information about the atmospheres and surface conditions of exoplanets throughout our galaxy. As this data accumulates, we may discover that truly Earth-like worlds are even rarer than our most conservative estimates have suggested, making our own planet not just precious, but perhaps irreplaceable as a laboratory for studying how intelligence and consciousness can emerge from the quantum mechanical dance of atoms and molecules. Tonight, as you prepare for sleep on your small blue world, remember that you rest upon something far more extraordinary than just a ball of rock orbiting an ordinary star. You exist on a cosmic miracle, a world where countless variables have aligned with mathematical precision to create the only known environment where matter has organized itself into patterns complex enough to contemplate their own existence and wonder about their place in the vast, mysterious universe that surrounds us. The gentle gravity that holds you safely to Earth's surface, the breathable atmosphere that sustains your every breath, the magnetic field that shields you from cosmic radiation, and the stable climate that has nurtured the evolution of life for billions of years all exist within incredibly narrow ranges that make our world a unique sanctuary in what may be a largely lifeless cosmos. And as you drift towards sleep, carried by rhythms that have remained constant throughout Earth's long history, you can rest in the knowledge that you are part of something magnificent and rare, a temporary arrangement of stardust that has achieved the remarkable feat of consciousness on the only world we know where such consciousness is possible. The universe may be vast beyond comprehension, but there is perhaps nowhere else in all that immensity quite like the small, perfectly balanced world that cradles you tonight. Tonight, as we draw toward the end of our cosmic journey through this impossible world, we find ourselves confronting perhaps the most humbling truth of all. The transformation we've explored tonight isn't just a thought experiment about planetary physics or gravitational dynamics. It's a revelation about the knife-edge balance upon which all existence depends. A cosmic reminder that the universe we inhabit operates within tolerances so precise that they make the finest clockwork seem clumsy by comparison. Every breath you take as you listen to these words depends on atmospheric pressure that exists within a range of just a few percentage points. Step outside those boundaries, and the delicate process of oxygen exchange in your lungs would cease to function. The water in your cells would either boil away into vapor or freeze into ice crystals that would shatter cellular walls like glass. The chemical reactions that power your thoughts would slow to a crawl or accelerate beyond control until the very molecules of consciousness dissolved into chaos. The gravity that keeps your feet planted firmly on the ground exerts exactly the right force to allow your heart to pump blood to your brain while permitting your bones to support your weight. Increase that force by even a factor of 2, and the human body becomes an impossible biological architecture, crushed under its own mass. Decrease it significantly, and our bones would weaken, our cardiovascular system would struggle to maintain pressure, and the very structure of life as we know it would begin to unravel. But perhaps most remarkable of all is the realization that these precise conditions aren't just random accidents or cosmic coincidences. They emerge from deep mathematical relationships that connect the smallest quantum particles to the largest galactic structures. The same fundamental constants that govern how electrons orbit atomic nuclei also determine how planets orbit stars, and how galaxies spiral through space. Change any one of these constants by even tiny amounts, and the universe becomes a place where stars cannot form, where atoms cannot bind together, where the complex chemistry of life becomes physically impossible. The electromagnetic force that holds molecules together, the strong nuclear force that binds atomic nuclei, the gravitational force that shapes cosmic structures, all exist in perfect mathematical harmony that allows complexity to emerge from simplicity. Our sun-sized Earth represents what happens when we push just one variable beyond its natural limits while leaving all others unchanged. The cascading failures we've explored tonight demonstrate how tightly coupled all the systems that support life really are. Change the planet's mass and you affect its gravity. Change its gravity and you alter its atmosphere. Change its atmosphere and you transform its chemistry. Change its chemistry and you eliminate any possibility of biological processes. This interconnectedness extends far beyond our planet to encompass the entire cosmic environment that makes Earth habitable. The sun burns with exactly the right intensity to provide energy for photosynthesis without sterilizing our planet's surface. Jupiter acts as a gravitational shield that deflects dangerous asteroids away from the inner solar system. Our moon stabilizes Earth's axial tilt, preventing climate variations that would make complex ecosystems impossible. Even the position of our solar system within the Milky Way galaxy appears to be precisely calibrated for habitability. We orbit our galactic center at just the right distance to avoid the intense radiation and gravitational disruption of the galactic core, while remaining within the galactic habitable zone, where heavy elements necessary for rocky planet formation are abundant enough to create worlds like Earth. The timing of our emergence as a species also appears to fall within a narrow window of cosmic habitability. Too early in the universe's history, and there wouldn't have been enough heavy elements to form rocky planets. Too late, and the expansion of space would have carried neighboring galaxies so far away that we would see only darkness beyond our local group, never suspecting the vast cosmic web that connects billions of galaxies across space and time. As we contemplate these layers upon layers of apparent fine-tuning, we're forced to confront profound questions about the nature of existence itself. Are we the beneficiaries of an extraordinary cosmic lottery, the unlikely winners in a game where billions of planetary systems failed to achieve the precise conditions necessary for life? Or does our existence point to deeper principles of cosmic evolution that we're only beginning to understand? Some scientists propose that we live in one of countless parallel universes, each with different physical laws and constants. In this multiverse scenario, we observe our universe to have life-friendly properties simply because we exist to observe them. Universes hostile to life would contain no observers to note their hostility. This anthropic explanation suggests that our apparently fine-tuned cosmos is actually just one random configuration among infinite possibilities. Others suggest that the laws of physics themselves might evolve and change over cosmic time, with our current physical constants representing a temporary equilibrium that allows complexity to flourish. In this view, the universe passes through different phases of physical law, sometimes permitting the emergence of stars and planets and life. Other times creating conditions where only the simplest forms of matter can exist. Still others propose that consciousness itself plays a fundamental role in shaping the physical properties of the universe, that the act of observation somehow participates in determining what becomes real. This quantum mechanical perspective suggests that the boundary between observer and observed, between mind and matter, may be far more fluid than our everyday experience suggests. But regardless of which theoretical framework we embrace, the practical reality remains the same. We find ourselves existing in a universe where the conditions for life exist within incredibly narrow ranges, on a planet whose size, composition, and cosmic environment fall within even narrower limits that permit the emergence of conscious beings capable of contemplating their own existence. The responsibility that comes with this realization is both humbling and inspiring. If Earth truly represents the only known oasis of life in our local cosmic neighborhood, then every species that shares our world, every ecosystem that has evolved over billions of years, every genetic sequence that has been preserved through countless generations of natural selection, represents an irreplaceable treasure of cosmic significance. The extinction of a single species doesn't just represent the loss of one form of life, but the elimination of a unique solution to the challenge of existence that required billions of years of evolutionary experimentation to discover. The destruction of an ecosystem doesn't just harm local environments, but removes complex networks of biological relationships that may never be recreated, even given geological timescales. Yet our exploration tonight also reveals reasons for profound optimism about the future of life and consciousness in the universe. The same mathematical precision that makes our current existence possible also suggests that the universe operates according to comprehensible principles that can be understood through patient scientific investigation. Each new discovery about the fundamental laws of physics, each breakthrough in our understanding of cosmic evolution, each insight into the conditions that permit complexity to emerge, brings us closer to answering the deepest questions about our place in the cosmic order. We are not just passive beneficiaries of cosmic fine-tuning, but active participants in the universe's ongoing attempt to understand itself. The technologies we're developing to study exoplanets and search for signs of life beyond Earth represent humanity's first tentative steps toward becoming a cosmic civilization. As we learn to detect Earth-like worlds around distant stars, as we develop the capability to analyze their atmospheric compositions and surface conditions, we begin the long process of determining whether the conditions that created life on Earth exist elsewhere in the galaxy. The discovery of even microbial life on other worlds would fundamentally transform our understanding of biology and our place in the cosmic community. It would suggest that the emergence of life, while requiring precise conditions, may be a more robust process than our current theories predict. Multiple independent origins of life would provide invaluable data about the range of conditions under which biological processes can begin and evolve. Conversely, the continued absence of detectable life elsewhere would reinforce the extraordinary rarity and value of the biosphere that surrounds us. It would suggest that Earth may indeed represent a unique cosmic laboratory where the universe has conducted a 4 billion-year experiment in the emergence of complexity and consciousness. Either outcome would carry profound implications for how we understand our responsibilities as the only known intelligent species in our cosmic neighborhood. The preservation of Earth's habitability becomes not just an environmental concern, but a cosmic imperative, ensuring that the remarkable experiment in consciousness that began with the first self-replicating molecules continues to unfold and explore new possibilities for complexity and understanding. As you prepare for sleep tonight, cradled by the gentle gravity of our perfectly sized world, breathing air held in place by precisely the right gravitational field, protected by magnetic fields generated by exactly the right planetary mass. Remember that you are part of something far more extraordinary than any science fiction could imagine. You are a conscious expression of cosmic evolution, a temporary arrangement of stellar debris that has achieved the remarkable feat of self-awareness. The atoms that form your body have journeyed across space and time, from the hearts of ancient stars to this moment of contemplation. The calcium in your bones was forged in supernova explosions that occurred billions of years ago. The iron in your blood was created in stellar cores that burned for millions of years before scattering their contents across interstellar space. The carbon that forms the backbone of every organic molecule in your body was synthesized in the nuclear furnaces of stars that died before our sun was born. You are not separate from the cosmos, but intimately connected to its deepest processes. Every heartbeat resonates with rhythms that have echoed through cosmic history. Every thought participates in the universe's ongoing evolution toward greater complexity and understanding. Every moment of consciousness represents a victory over the vast forces of entropy that seek to reduce all complexity to uniform simplicity. The question we began with tonight, what would happen if Earth was as big as the Sun, has taken us on a journey through physics and chemistry, through space and time, through the fundamental forces that shape reality itself. We've discovered that our world exists in a state of perfect cosmic balance, neither too large nor too small, neither too hot nor too cold, with exactly the right gravitational field, exactly the right magnetic protection, exactly the right atmospheric composition to allow the miracle of life to unfold. But perhaps more importantly, we've learned that we are not just observers of this cosmic ballet, but active participants in its ongoing performance. Through our curiosity, our scientific investigations, our growing understanding of the universe around us, we extend the cosmos's capacity for self-awareness and self-understanding. So as we reach the end of our cosmic journey together, we're left with a profound realization that changes everything about how we see our place in the universe. Tonight, we've witnessed what would happen if Earth was as big as the Sun, and in doing so, we've discovered something far more extraordinary than we ever imagined. Our small blue world isn't just lucky to exist. It's a cosmic miracle balanced on the knife's edge of physical possibility. Every breath you take, every heartbeat, every moment of consciousness depends on our planet being exactly the right size, in exactly the right place, with exactly the right conditions to allow the impossible beauty of life to flourish. Sweet dreams, fellow travelers in this magnificent cosmos. Until we meet again among the stars.